Hi everyone, in this tutorial I'm going to show you how to use the latest version of Phoenix FD, that's version 2.2, to create carpet bombing. So before we begin, here is the result that we're chasing. It's a series of explosions. First off, I'm going to show you how to set up a single one of those explosions, and then we'll just multiply them and make them work together. And finally I'm going to show you just a little bit about the render settings. Okay, so how do we begin? First off, we need to create a Phoenix FD simulator. We'll make it wide and not quite tall, because we'll need a larger area. And we need to create our emitter geometry. We will use a sphere for those explosions. Its size in our case should be between 2 and 3. I will choose this one. And in order to emit the explosion, we're going to go to the helpers tab, and here from Phoenix FD we're going to pick a Phoenix source. So Phoenix source is the invisible object that feeds the emitters with temperature, smoke, and velocity particles or other stuff. So we're going to add the sphere here to the target objects list. And this is the basic Phoenix setup. So if we go here to the modify and start the simulation, our sphere will start burning, which is the default mode with the default settings, before we change anything. Okay, so here it is. It starts to burn and to emit smoke. In order to make it more like an explosion, first off we're going to exclude it from interacting with the simulator. This means that it will not be an obstacle anymore, because until now it was standing in the way of the velocities and of the fire and the smoke, and they had to go around it. So after we exclude it, so it will just take the role of a source and not an obstacle, and we need to set the mode of the source to inject, and also to increase its discharge quite a lot, so that will have an explosive effect right here. You can see that now it emits much more temperature and much more smoke in the same time. Here it is. But we will need to change the limits of our grid. We will choose right here from the adaptive grid motion, from the adaptive grid option, we will set it to speed, and this means that if we run the simulation again, the grid will start expanding around cells where there is higher speed, and here is a threshold actually of the speed, of the velocity that Phoenix FD will look for. Okay, so we'll stop it right now because we've had a too big expansion. We will change the way the animation works by animating it to emit with even larger discharge, but just for a single frame. So I will zero it out and we'll go to about frame 5 or 6. I'll set the discharge to 3000. The temperature and the smoke are fine for now, and we will even stick for those until the end of the tutorial. And then the discharge, we'll set it back to 0. So it will not discharge, and on the 6th frame it will burst out an explosion with discharge 3000 and then stop again. So the effect we can see immediately right here. So here it is. We create an expanding fireball in the beginning that blows up just in the single frame, and then it starts to cool off and rise up. Let's see it in real time. Okay. So that's more like it. I'll also lower the grid so that the sphere is inside it from the very beginning, because otherwise we get interaction with the borders of the grid, because the grid does not manage to expand so quickly as our explosion goes. Okay, so now the shape of the explosion does not get distorted by the borders of the grid. Here it is. But we will distort it with something else. We will put a box underneath the simulator that will serve as the ground, like this, and this way we will have a more proper interaction of the explosion with the ground, because the carpet bombing interacts with the ground in real world. Okay, so here it is. In order to have a better look of the simulation, because the viewport preview is good enough, but we can do even better. Right here, we're going to enable from the extended viewports the Phoenix FD GPU preview. So here it is. It works when we have selected the simulator, and it shows with much better quality the content of the simulator, and it works only for the Phoenix FD simulator. It does not show the surrounding geometry, but it will be good enough for us to have a better look at what's going on. Right now we see only the emissive part, because we don't have any whites yet in the scene. So we're going to create a standard omni white and just put it somewhere for now. Okay. And after we've created the white, we need to tell Phoenix to use it. So here from the preview settings, whiting is enabled by default, and we'll just pick the omni white, and we can see the smoke is also visible in the GPU preview right now. We just need to set a couple of options on the on the omni white. We need to enable shadows and use ray trace shadows, and also we need to enable the atmosphere shadows. So this way the smoke will be shaded better. You have to do this every time you use a lamp for the GPU preview. And also this affects the production rendering of Phoenix. So right here it is. Otherwise, if you don't enable those options, you won't have the atmospheric shadows, and the smoke will look flat. We will need to make the smoke a bit less transparent, because we will be doing a massive scale explosion that just has to look a bit more epic. So you can see that here, as we modify the option, we get real-time preview in the GPU window. We'll set it to 0.9 because we need a very thick smoke to make it look massive. Okay. Okay, so the next thing I'm going to do is to lower the ground a little bit so that it doesn't intersect with our emitter. I will just move the source out of the way, and now I'll run the simulation again to see the result. So here it is. You can see that our simple explosion interacts with the ground and starts to spread out as it hits the ground, and then it starts to raise up because it's hot and the temperature drives it upwards. Okay, so we'll wait for it just a little bit more. You can see that it naturally starts to form a mushroom cloud right here, but in our scenario right here we're not going to make use of it. So just let's look at it in real time. Okay, so you can see that it spreads out and then it rises up. So from now on we'll need more of this spreading out and less of the rising up, because this is how the carpet bombing works. The explosion spreads out on the ground. This is the natural physically accurate effect of the carpet bombing. So in order to slow it down and prevent it from rising up like this, we're going to use here the unit setup and increase the unit scale to 4 meters. So this means that each cell of the simulator will be 4 meters wide. So you can see right here on the edge of the grid the size of the cell right now. Later on we're going to refine the resolution. Actually right now I'm going to just increase it, and you can see that here the green grid is the one that we're modifying, and the red one is the result from the adaptation from the previous simulation. So you can see that as we're increasing or decreasing the resolution, the grid gets much finer cells, and we'll get much finer detail, but our simulation time will increase. So I'll just leave the cell size to 0.8. So in order to get the real world size of the explosion, you have to multiply 4 meters by 0.8 by the size of the simulator. And if you want to really accurately model real world explosions, this will help you a lot. Okay, so let's see what we've got so far. Here's our initial fireball. Again, it starts to spread out, but this time it does not rise. Actually, it does rise, but it rises in a much lower rate than before. So you can play with this parameter if you want to speed up or slow down the rising of your simulation. The next thing we will do is you can see that we're getting this fuzzy effect on top of our explosion, and the reason for this is here from the dynamics tab. There is this vorticity parameter. So naturally fluid simulations lose detail over time, and the vorticity option here it introduces more vortices in the explosion or in the simulations in general. So the problem with it is that if you add too much vorticity, you're starting to get the surface of your fluid torn up like this here, and this happens with time. The more time passes, the more fuzzier it becomes. So we'll just zero it out for now. We will use it later, but let's see the basic result without this parameter. And right now we should get a really smooth shape of our explosion. So right now it's really early to say that this is an explosion, but we're going to adjust the dynamic settings and the settings of the simulation in order to get the desired effect. Okay, so let's look at it in real time. So it spreads out, but you can see that our result is not quite symmetrical, or not symmetric at all. So the next thing we need to do is right here from the conservation panel to increase the quality to 50. So in short, conservation is the force that makes all fluids, smoke and liquids to just swirl around as they are moving. And in nature, the quality of conservation is an infinite number. So all the fluids are entirely made up of spinning vortices. Because we're doing a numerical simulation here, the more quality that we need to introduce, the more calculations and the slower the simulation runs. So by default it's 8, but this is not enough for our simulation right now, so we're going to use 50. Also Phoenix FD has several methods of conservation. For our purposes right now, the default symmetric conservation is the best, because it does what it's named after. It produces a very symmetric simulation as long as you have a symmetric emitter, and it's very useful for explosions like this one and for nuclear explosions, and you get a really high amount of symmetry with it, as long as your quality is high as well. Also there is the smooth conservation that is mainly used for liquids, and the buffered conservation, which is okay for random chaotic fire simulations where you don't need much symmetry. Okay, so now we see that we have added a bit more symmetry. So here our explosion has reached the border of the simulator, and it has deformed, but this will be enough in our case. So from now on we have to start increasing the detail of the simulation, because right now it's perfectly smooth and flat, and that's not how things look like in the real world. So we will change the material transfer method here to multipass. Multipass is the same as the default classic method, but it gives more details as the fluid flows around the simulator, and it keeps much of this energy of these vortices that here the vorticity option tries to recover. So in my opinion the multipass method is better, but it requires more calculations, so your simulation will run a bit slower, and but just a little bit. And here we will reduce the steps per frame to just 1. We need more steps per frame when we are simulating liquids, but for the explosions 1 is just fine. Okay, so here you can see that we immediately get much more detail, even without any kind of artificial vorticity confinement. Also, the next thing we need to do is right here to enable the uniform density option. When you have not enabled it, you are basically in simulation mode that is again closer to liquids. Without the uniform density option, the fluid tends to behave and form more spherical structures, so it doesn't tear apart like you see right now when we have changed the option. And I think right now the result is much better, and this is what we're going to use from now on in our final simulation. So you can see that because we have increased the conservation, the explosion interacts much more with the borders of the simulator, and and this is actually the effect of increasing the conservation. You have the butterfly effect, where each portion, each piece of ground in the simulator produces changes everywhere around the simulator, and if you are near the borders, you will get deformed results. So you need to be careful about this, and I will just increase the size of the simulator a bit in order to prevent this. We have to be careful not to increase the size not to make the simulator bigger than the ground below. So let's see the result again. Okay, so these are the basic elements. The explosions start to spread out on the ground, forms this little shock wave around it, and the force of the conservation even pulls it down a little bit, but after a moment it will start rising up because it's still very hot. You can also control the speed of rising up here with the cooling option. So if your fluid is too hot, it will rise up faster, and if you want to slow it down over time, you can start with a hot fluid. Here from the Phoenix source you can increase the temperature, and you can, for example, increase the cooling right here. So you start with a very hot fluid, and then it will cool down fast and slow down its descent, its ascent. So let's see our result in real time. So here it is. We have a bit more spreading than we want. So the way to control this is to move the ground underneath higher or lower. If we move it this much, we will get almost no spreading at all, because right now the emitter is far from the ground and it interacts with it much less. Okay, here it is, and right now we don't get any kind of spreading or shockwave on the ground at all. Here it is in real time, but for really short. So it starts to rise up slowly, and it doesn't collide with the ground at all. So I'll just put the ground back where it was. Another method to control the spreading out is to change the shape of the emitter to a bit more elliptical, like this. So this way you have more normals, and the velocity coming out of this shape will more of it will point upwards and downwards. You will channel the velocity vertically instead of horizontally. So let's see the result of it right here. This way the fireball will shoot up and down and less to the sides. So if you're worried about getting too much of the spreading of the explosion, you can control it by changing how elliptical the emitter is. So right here you can see that we have some spreading on the ground, but the mass of the fireball is not affected. It's not sucked up to the ground as much as it was before, and it starts rising up. I'll just pause the recording until the simulation is finished so I can show you. Alright, so this is how it looks for now. And you can see that it's rising too much, so I'll just move the ground a bit closer and reduce the amount of ellipticity. And the next thing we need to do is a technique that I favor from my research on nuclear explosions, which will not be quite essential to the dynamics of the simulation right here, but it will help the look of it. We will create a layer of smoke on the ground that will imitate the dust and the soil and the particles that lay on the ground, and it will be affected by the explosions, and you will see the result. Okay, so we will create another box like this, and this thickness is enough, and we will need another source. Right here. We will use this time the brush mode, and we will imprint a neutral temperature, which is 300 degrees Kelvin. The temperatures in Phoenix are in Kelvin, and 300 is assumed to be 0 Celsius. So with this temperature, the smoke will not go up, and if it's below 300, it will actually start to go down. But using exactly 300, will make the smoke independent of the temperature, and it will not rise up or go down, and we'll print the amount of smoke, which is 1. 1 is fully smoky. You can actually even set it higher than this, and as the simulation flows, as the fluid flows around the simulator, you will get much thicker smoke because it will not dissipate, because it will have a reserve above 1. So if we're using the brush mode, here the discharge is treated as percentage, so we'll use 100%, and then we will imprint this temperature and this amount of smoke in the simulator. We just need to pick the box, and also we will need to exclude it from interacting with the simulator, so it will not be an obstacle, but just used for brushing. Okay, here it is, and I'll make it a bit more invisible and also not renderable. I'll display it as box as it is. So let's see what we got now, right now. You can see that here, because of the high conservation, we get a bit of a shockwave that spreads around. Okay. Whoops. So here it is. This will serve much better when you see the final result. So I'm just going to lower the to actually move the ground up even more, because our explosion is still moving up too fast. and this should be the final adjustment before we multiply the emitters and the sources. Okay, I think that will do. So I will just tweak an option here in the preview settings so that we see the content of the simulator only when it's selected, because our viewport wags a bit because of this. And now the next thing we need to do is to create more emitters. So I'll place another one here. The larger the emitter is, the stronger the explosion will be. So I'll just create a path right here from these exploding emitters. How much we get? Now just put another one here. And no, I'll just put it here. Okay. Let's adjust the grid a little bit so that all the emitters are inside it, and okay. So I will revert right here the scale of the original emitter, and I will scale all of them after this. Okay. So next thing we need to do is to multiply here the Phoenix sources, the Phoenix source into many Phoenix sources. I will clone this one again. We need 8 of them for each emitter. Okay, and one more. Alright, so for each one we have to remove the original emitter and add the one that we need. Whoops, we don't want to emit from the box, we want to emit from the sphere. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And we need to exclude the spheres from interacting with the simulator. Okay, and now in order to accomplish the animation, we have, since we have cloned each of these sources, we have the animation here of the discharge. So we'll just offset it later in time for each one of them. This one later, even later. Okay. $65, $80, and then about $90. I think this should work. So, in order to preview the result of the animation, let's just decrease the resolution a lot and just see when the explosions go off. Now, don't be worried by the shape of the explosions right now, because we have a very low resolution, and you can see right here the cell size is each of our emitters is actually made up of no more than 10 cells, so the velocities are pointing in very strange directions, and the behavior of the explosion will not be the one that we have modeled so far. And as we increase the resolution later on, we will have even better effects than the explosion that we have adjusted so far. So just ignore this shape, and we just need to preview the dynamics and the timing, and I think this will be okay. I would just increase the animation with about 20 frames and I think this should do. Alright, and here's our final explosion. I think I should make the grid even wider on this side. Okay, so let's just preview the animation again, and to me it looks okay. I think that's the correct timing of the explosion, of the sequence of the explosions. So what we're going to do next is increase the resolution to an average value. Right now we have a total of 3.5 million cells, which is good for a first control run of the simulation. And I will just pause the recording a bit for a while, and then show you the result. Okay, so here we are, and this is the result of the simulation. Here I'm using virtual dub to gather together into a clip the PNG files that the GPU preview exports by default. That's a very cool feature of Phoenix, and right here from the preview tab, the GPU preview saved during simulation, that one's ticked by default, so it creates a PNG file for each frame from the GPU preview, and it's a very useful feature to just quickly track the dynamics of the simulation without having to render it explicitly. So here it is. So I made a couple of changes before I got this result here. So the first thing was that I increased the resolution just by one click here. So now the cell size is 0.5, and even though I increase the resolution, you can see that we are not getting much detail right here. So in order to get it, it's finally time to enable the verticity option that we disabled in the beginning. So I'm going to set it to 0.05. It was 0.5 in the beginning, but that's way too much, and our smoke is going to start to tear up. And another thing is that we're going to add a bit of random noise to the simulation to make it more chaotic. So before I run again, another change that I made was that I animated the discharge of the Phoenix source that created the thin layer of smoke on top of the ground. I animated it in the manner that we animated the other the emitters for the explosions. So it will emit the smoke with 100% discharge in the zeroth frame, and then it will stop emitting So I've done this in order to avoid conflicts between the emission of the smoke and the emission of temperature, the injection of temperature here for the explosion emitters, because you can't tell in which way Phoenix is going to evaluate those sources. It should be done in the order that you've created, but just in order to make sure that you don't get any conflicts, it's good to emit separately and build the smoke layer separately from the explosions. Otherwise, the part of the emitters here that is underneath the smoke layer might get erased if the smoke emitter emits afterwards the explosion has gone off. So this way you will get actually twice weaker explosion than it was supposed to be. So just making sure that we don't get any problems by animating the discharge. And so after I've added the vorticity and the randomization, I'm going to run the simulation once again, pause it, and then return with the results. Okay, so this is the result. And once again, you can see that right here we need to adjust the discharge of the third explosion, because it's too weak, and I will increase as well the last one. So we will increase the discharge by actually increasing the radius of the emitter. Okay, so this should do, and I'll run the simulation again. Okay, so here is the result. We see that two of the explosions are still moving downwards, so in order to fix this, I will just move the solid ground downwards a bit. I've also made changes to the view during the simulation, and if you are messing around the views or changing the viewports, the GPU preview exports the PNGs just as they are at the moment of the simulation frame, so your animation may get messed up. So if you want to export a clean animation, you may go to the preview tab and select the interval. So in my case from 0 to 120, and just click save to export a fresh animation, and this is what I did for the final animation, the most latest one. Because I have been making changes, I moved the Y to the left and made some changes to the field of view to get a better perspective on the simulation. So now I'm going to run this again. Okay, so I had to make a couple of changes on the simulation. The first was that I moved the ground downwards a bit, because two of the explosions were too flat, and I also changed the perspective in the viewport. I changed the field of view and the zoom, and I moved the white emitter to the left. So while the simulation unfolds, and before we increase the resolution to the final resolution, I'm just going to go briefly through some of the rendering options right here. And still, while we are simulating on a lower resolution, we can make some quick renders that will not take as much time as when we increase the resolution. So we have been here in the render parameters dialog before to set the smoke density to 0.9, but now we're going to talk about the fire aspect of the explosions. So we're going to, if we render with the production, with the scanline renderer right now, we see pretty much the same or very close result to the one that we see in the GPU preview. I'm using the scanline renderer right now, but the Phoenix FD can also make use of the V-Ray renderer, and actually it has some more options for it that will make things even prettier, but scanline will do for now. And the thing that I want to show you is right here. If we click on the white option, we enable the emission of white from the fluid. So all the areas that are bright and hot and burning will will start emitting white. That will light up both the simulator itself and the surrounding geometry. So this is done by placing white sources inside of the simulator, of the grid, and Phoenix FD does this for you. It has several options for placing. Simple is a simple spherical placing of whites. If we click preview placing right now, it will calculate and show you where the white sources are. Also, we have from here you can choose the amount, the count of whites that we will be using. So I'll set this, for example, to 200, but I'll just keep it to 20 in order to just show you the basics of this option. Whoops, no. I'll save that for later. If we click preview placing, and if you render, you start seeing these blue spheres in the viewport that show where the whites are. So if you choose to use more whites, they will be smaller, and they will fit better in the most emissive areas, but it will take more time to render the scene. So you can place many whites here, but it will get smaller. So I'll be just returning to 20, and the inside option places places the white sources using an advanced algorithm, and it chooses the most appropriate places for them and the most appropriate sizes. You can also play with the size and with the power of the white sources with these two options here, but that's only in case that the default size and power does not fit your simulation. So the final option is this one, the reduced grid. It just places the white emitters inside the grid, but you can choose the percentage of grid reduction right here. You can set it to 100, and then each cell that that has an emissive component to it will become a white, and this will be quite heavy, and it might take a lot of time to render. So by default this option is just set to 10%. If we click preview placing here just to calculate the whites, and here they are. They're much more. If you if you reduce the grid further, they will start getting bigger. We're previewing while the simulation is running, so our placement is erased by the time the next frame is calculated. So the problem with the inside option is that when you are rendering an animation, you may get some flickering with it. So with the reduced grid option you don't get this, but if you reduce the grid too much, you might get too smooth of shading. So there's a practical limit on how much you can reduce it, but it depends on the scene that you're making, so you have to adjust this by yourself. So I'm going to use 10% for now, and for the self-shadowing, this option controls how the how the fluid itself stops the propagation of white, and it will start to cast shadows on itself from its own white. So you may not use it, or you may use the ray traced self shadowing, but it will produce noise just as and just as any ray traced rendering. You have to wait for it and increase the quality settings in order to remove this noise. And there is another new option in Phoenix FD 2.2, that is the grid-based self-shadowing. So it uses this same grid reduction here, and it uses a different algorithm to self-shadow itself. This does not affect the surrounding geometry. We're still using the additional emissive whites to shade the surrounding geometry, but these additional whites will not shade the simulator itself, and this algorithm will be used. So let's just preview it and see the result here with these settings. So here you see that now we have some illumination of the fluid, and here you can see the glow that is produced on the ground when the explosion lights it up. So also you can see here the effect of the smoke layer that we've placed on the ground. You can see that we're getting these shock waves forming around the explosions. So if you want to increase the strength of the white, you can play here with this graphic. It says that how much temperature, how much white is emitted depending on the temperature of the cell. So right now we're emitting with 2000 degrees, so you can see it here. So this is the amount of white that you can that we are emitting. So you can play with these parameters, and you will see the result live in the GPU preview. So if we're modifying it like this, here we see the difference, but you will not be able to see the preview of the emissive whites, so we will still have to render. Okay, so in the beginning we just wait a little bit until the white positions are calculated, and you see that now we have a much brighter explosions than we had with the default settings. I will just reset here the settings of the emission, because I don't want to mess with the emissive graphic here. So now I'll just enable whites again, and I'll set this to grid based and to reduce grid. And if you just want to plainly increase the strength of the emission, you can just set this multiplier right here to something like 10, for example. Okay, so it's taking a bit of time to calculate because we are running the simulation simultaneously underneath. And so here it is. Right now we have uniform scaling of the white, so not only we have not just increased the brightest areas, but all of the areas that are emitting white. And this is it. One more thing that we can do is to set the color of the smoke to a little more brownish, because gray is not a natural color for the ground explosion that we are creating right now. So I'll just set it to something like this. So when we do this, we will get a more reddish tint on the color. Let's see now. So here it is. And in my opinion, I think that that's a bit more pleasant to look at, and it depends on your setup and the way that you want to implement this. And there's one more thing. Here we have the scattering option. It says it just uh, how is the white propagated inside the smoke. So if you disable the scattering, the smoke will act more like a solid body. And if you want your smoke to look more like vapor or clouds, and it's recommended that you use the analytic scattering. So here you have the option with and without shadows. I'll just use the shadow one, and this way the white travels more through the smoke, and it simulates the scattering of the white that happens in real world with an analytic formula. So in general you will get a more kind of transparent smoke, and the white will travel a greater distance, and it will look more realistic for vapor or clouds. And I think that it works better with this scene, so I'm going to stick with analytic. But if you disable it, I'm just going to show you the result. We'll get a result that looks like more thicker smoke, and here it is. The white is obstructed more, and it's the smoke is not glowing that much. So I will return it to analytic, but you can do whatever you like with your setups, and adjust them accordingly to the result that needs to happen. So this is it. I'm just going to wait for the simulation to end and then continue. Alright, so our simulation is complete, and this is the result. And you can see right here that as we were making changes to the colors of the simulation, they were captured by the GPU preview, and you can even get more distortions if you are rotating the preview or changing the viewports. So in case you're not happy with the way the sequence is exported, or in case you have messed up with the views, you can always export it later. Right here from the preview tab you can select the interval from 0 to 120 and click save, and it will automatically go through all the frames, render them in the GPU preview, and save them. Okay, so again, this is the result, and I think this should do for our current resolution. I would just render this sequence with white ink, and then I'll be back, and we will finally upscale the simulation to the final resolution, and we will render the final result. But right now we'll just do a quick control control render to see how the simulation will look with emissive whites. And also, before we start to render, we have to make sure that right here in the object properties of the emitters, we have made them not renderable. So that's it. I will be back with the results shortly. So here we are, and this is the result of the animation. The render time was about 25 minutes on my i7. So I still need to make some adjustments. First of all, you can see that the fire takes a bit too much time to cool off. So I'm going to go to the dynamic setting and increase the cooling to 0.1. This means that the explosions will cool off faster, and they will not be this bright for so long. So the next thing that I want to do is just to increase the strength of some of the explosions even more, to make it a bit over the top, because that makes it more impressive. So I'm going to scale this one a bit. It's 3.5, 3.6. This one as well. Now make it about 4. Okay, this one is pretty small as well, so maybe I'll even make it the biggest one, like this. And the next final still needs a lot of boost. Okay, and one more thing that I want to do is just to regulate the timing of the explosions, because now they're pretty evenly spread. So I will make this one wait for a bit longer, and this one as well. Okay, so 1, 2, 3. Okay, so we still have some. I'll try to make this more irregular. Okay, so these two are okay. So I'll run the simulation again and render and come back with the result. Okay, so here is the intermediate result, and I think I'm happy with this result so far. So finally I'm going to increase the resolution and the resolution of the simulation, and then the rendering resolution, and we'll make our final simulation and our final render. So we could just increase the cooling just a little bit more, but I will keep it as it is. So what we're gonna do next, here I'm going to increase it to 50 million cells. Also in the preview options I'm going to increase the level of detail, because with such a high resolution we are going to run out of memory, and it's going to become quite slow. So here it is. I'm going to increase the level of detail to about 3 or 4. I'll set it to 4. Now if we need more detail I will decrease it later. That's just the preview option. It doesn't affect the simulation or the rendering in any way. And I'm also going to increase the length of the animation to 200. And so we are ready, and I will be back with the final results. Okay, and here's the high resolution carpet bombing. So you see that I think things worked out pretty well. I still have a couple of suggestions. So first of all, the one thing I needed to change before I start rendering was here to decrease the emissive multiplier, because we increase the resolution, the emission is defined per cell, so when we increase the cells we need to reduce the multiplier, otherwise the emission becomes too strong. So next thing is that you can see that our explosions pretty much retain their spherical shape and do not get so distorted as before, as the low resolution version. Now the reason for this is because when we increase the resolution, each of our emitters here, their shape is much better translated than with finer cells. So this way the shape of what they emit will follow much better their own shape. So if you want to distort the shape of the explosions, you need to further increase here the randomization, or you need to add noise to the shape of the emitter in order to achieve that. So one more thing is that our fire rises too high before it cools off. Now this might be a desired effect, or in case you don't want it and want to see how it will work without this much fire and with faster cooling, I'm going to increase the cooling parameter here to 0.3, and I'm going to run the simulation and the rendering once again just to compare the results. Also, another change I'm going to make is to bring here the emitters closer to each other so that they interact more, and we don't have these separate clearly visible fireballs, but I hope that in this way I can achieve a more violent effect of the series of explosions, and have them interact more and interfere with each other. And I'm also going to fix the camera as soon as the simulation is ready. So I'm going to run this once again and then come back with the results. So here's the final result of our tutorial, and I think there's a little more that could be done on the cooling side. If you like, you can experiment with this and increase the cooling to 1, for example, and be more radical with it. But in this case, we won't have that much of this cool shading here that I'm kind of fond of. So that's it, and the final simulation time was about 4 hours on my Intel i7, and the rendering time was about 5 hours. That's for 200 frames. So I would like to thank you for watching, and see you next time.